we look up at the night sky, it often feels quiet and simple. A few bright stars appear scattered across the darkness, each one shining gently from far away. For most of human history, that was all people could see. The stars looked like distant points of light, almost like small holes in the sky. But the reality is very different. Those points of light are not small at all. Each one is an enormous star, many of them larger than our sun. And together, these stars belong to a vast structure that surrounds us. That structure is called the Milky Way galaxy. Our sun is just one member of this enormous system. It is one star among hundreds of billions of others. Many of those stars have their own planets, their own systems, and their own stories unfolding across space. The Milky Way stretches across the universe in a wide spiral shape made of stars, clouds of gas, and drifting dust. When scientists study it, they find that it is not a small neighborhood of stars. Instead, it is a gigantic cosmic city filled with stellar systems spread across an almost unimaginable distance. And our solar system sits quietly inside it. We are not near the center of the Milky Way. We are also not close to its outer edge. Instead, our sun lives in a middle region of the galaxy, orbiting slowly along with billions of other stars. All of these stars are moving together around the galaxy's center, each following its own long path through space. From our position here on Earth, we cannot easily see the full shape of the Milky Way. We are inside it, surrounded by its stars. This makes it difficult to step back and look at the whole structure at once. But we can still ask an interesting question. What would it take to travel across the Milky Way? Imagine beginning your journey near one outer region of the galaxy. You set a course toward the opposite side, heading through billions of stars and vast clouds of gas. The trip would take you past star clusters, through spiral arms, and eventually across the crowded central regions where stars are packed much closer together. Then you would continue onward, leaving the center behind and traveling out toward the distant outer edge on the far side of the galaxy. Even imagining such a journey begins to stretch our understanding of distance. The space between stars is enormous. Even the nearest stars to our sun are separated by distances so large that human spacecraft would need thousands of years to reach them. But the Milky Way is not just a collection of a few nearby stars. It contains hundreds of billions of them spread across a huge region of space. Traveling from one edge of this galaxy to the other would mean crossing one of the largest structures we can observe directly from Earth. For many centuries, people did not realize that the Milky Way was a galaxy at all. Ancient observers simply saw a glowing band stretching across the night sky. This pale ribbon of light was visible on very dark nights, far away from city lights. Because it looked like spilled milk across the sky, many cultures gave it names related to milk or mist. The term Milky Way itself comes from an old Latin phrase meaning Milky Road. Today, we know that this glowing band is made from the combined light of billions of distant stars. When we look along the flat disk of our galaxy, all of those stars blend together into the soft glowing band that crosses the sky. For astronomers, understanding this structure became an important challenge. Scientists wanted to know how the galaxy was shaped, how far it extended, and where our own solar system fit inside it. But measuring something as large as the Milky Way is not simple. Unlike distant galaxies that we can photograph from the outside, we are located within the Milky Way itself. Trying to measure its full size is a bit like trying to measure the size of a forest while standing among the trees. You can see the nearby trees clearly, but understanding the full shape of the forest takes careful observation and patience. Over the past century, astronomers have slowly built a clearer picture of the galaxy we live in. Using telescopes, careful measurements, and new technologies, they have begun to map the stars around us and estimate how far the Milky Way extends across space. And what they discovered revealed something remarkable. Our galaxy is far larger than anything humans experience in everyday life. To understand just how large it truly is, we first need to explore the special way astronomers measure distance across the universe. To understand the true size of our galaxy, we first need to talk about how distance is measured in space. On Earth, we usually measure distance using familiar units like meters, kilometers, or miles. These measurements work well for everyday travel. We might measure the distance between two cities in kilometers or the length of a road in miles. But when astronomers look out into space, these ordinary measurements quickly become difficult to use. The distances between stars are so large that writing them in kilometers would create numbers with many zeros. Even the nearest stars are separated from our Sun by trillions of kilometers. When scientists began studying these enormous distances, they realized that a different system would be much easier to use. Instead of measuring space using distance alone, astronomers often measure it using time. More specifically, they measure how long it takes for light to travel from one place to another. Light is the fastest thing we know of in the universe. In the empty vacuum of space, light travels at a speed of about 300,000 kilometers every second. This number is difficult to imagine, so it helps to compare it to something more familiar. At that speed, light could travel around the entire Earth about 7 times in a single second. In the time it takes you to blink your eyes, light could circle our planet several times. If we stretch that time out a little longer, the distances become even more impressive. In just 1 minute, light travels about 18 million kilometers. In 1 hour, light travels over 1 billion kilometers. These numbers already seem enormous, yet they still describe only short distances when we begin talking about the scale of the universe. Astronomers therefore often take the next step and measure how far light travels in an entire year. When light moves continuously for a full year at its incredible speed, it covers a distance of about 9.46 trillion kilometers. Scientists call this distance 1 light year. Despite its name, a light year is not a measure of time. It is a measure of distance. It simply tells us how far light can travel during 1 year. This unit turns out to be extremely useful when describing the distances between stars. For example, the nearest star system to our Sun is called Alpha Centauri. Even though it is the closest star system to us, it is still about 4.3 light years away. That means the light we see from Alpha Centauri tonight actually left that star more than 4 years ago. Many other stars are even farther away. Some stars that we can see in the night sky are hundreds of light years from Earth. Their light began traveling toward us centuries ago, long before modern technology existed. When astronomers observe distant stars or galaxies, they are often looking at light that has been traveling through space for very long periods of time. In this sense, looking deeper into space also means looking further back in time. The concept of the light year helps make these vast distances easier to understand. Instead of writing distances with trillions or quadrillions of kilometers, astronomers can simply describe how long light would need to travel to cross that distance. This gives a clearer sense of the scale involved. It also reminds us that space is not just about distance, but also about time. Light carries information from distant places across the universe. The farther away something is, the longer its light must travel to reach us. When we observe distant stars, we are seeing them as they existed years ago. When we observe distant galaxies, we may be seeing them as they existed millions or even billions of years in the past. This idea becomes especially important when we begin talking about the size of our own galaxy. The Milky Way is filled with stars that are separated by enormous distances. Measuring those distances requires units that match the scale of the galaxy itself. Light years allow astronomers to describe these distances in a way that is easier to understand. Once we start using light years as our ruler, we can begin to explore how far away different parts of the Milky Way actually are, and how vast our galaxy may truly be. When we measure distances here on Earth, we usually think about space in terms of length. A road might be 10 kilometers long. A city might be 50 kilometers away. These measurements are simple and familiar because the distances involved are relatively small. But space is not small. Even the nearest stars are separated by distances that are far beyond anything we experience in daily life. When scientists began trying to measure these distances, they quickly discovered that using kilometers or miles became difficult. The numbers grew extremely large. For example, 1 light year, the distance light travels in a single year, is about 9.46 trillion kilometers. That number alone already contains 12 zeros. Writing distances between stars using kilometers would require enormous numbers that are hard to read and hard to compare. Astronomers needed a more practical way to describe such distances. The solution was to measure space using the time it takes light to travel from one place to another. Since light moves at a constant speed through empty space, scientists can use it as a kind of universal measuring stick. If we know how fast light travels, then we can measure how long it takes for light to move between 2 points. From that time, we can determine the distance. This is why astronomers often describe distances using light seconds, light minutes, light hours, and light years. These units make it easier to picture how far away something is. For example, the Moon is about 1.3 light seconds away from Earth. That means light leaving the Moon takes about 1 1/3 seconds to reach us. When astronauts visited the Moon during the Apollo missions, radio signals traveling at the speed of light took a little over a second to travel between Earth and the spacecraft. The Sun is much farther away. Light from the Sun takes about 8 minutes to reach Earth. When you see sunlight shining on the ground, that light actually left the Sun 8 minutes earlier. If the Sun were to suddenly disappear, it would take 8 minutes before we would notice the change. These examples help show how time-based measurements can describe distance. Once we move beyond our solar system, the numbers grow even larger. The nearest star system to Earth, Alpha Centauri, is about 4.3 light years away. This means the light from that star takes more than 4 years to reach us. Many stars in our galaxy are hundreds or even thousands of light years away. Their light has been traveling through space for centuries or millennia before finally reaching Earth. This leads to an interesting idea. When astronomers observe distant objects, they are not seeing them exactly as they exist today. Instead, they are seeing them as they were when the light began its journey. Looking into space is also looking into the past. For nearby stars, the delay is only a few years. But for distant galaxies, the delay can be millions or even billions of years. In some cases, astronomers observe galaxies whose light began traveling toward Earth before our planet even existed. This time-based way of measuring space is one of the most fascinating aspects of astronomy. It means that every observation carries a piece of history with it. The concept of the light year allows scientists to describe these distances clearly. Instead of writing huge numbers in kilometers, they can simply say how many years light would need to travel between 2 points. This makes it easier to compare distances across the universe. A star 10 light years away is twice as far as a star 5 light years away. A galaxy 1 million light years away is much farther still. Using light years allows astronomers to scale distances naturally as they move from nearby stars to entire galaxies. This system becomes especially important when studying the Milky Way. Our galaxy contains hundreds of billions of stars spread across an enormous region of space. The distances between these stars are so large that light years become the most practical way to measure them. Once we begin thinking about distance in terms of light travel time, we can start asking much larger questions. For example, how far away are different regions of our galaxy? How long does it take for light to travel between them? And how long would it take to cross the Milky Way itself? Before we can answer those questions, we need to take a closer look at one particular part of our galaxy, the mysterious region at its center. If we want to understand the size of the Milky Way, one helpful place to begin is the center of our galaxy. The Milky Way is not just a loose cloud of stars. It has a structure, with many of its stars arranged in a wide spiral disk that circles around a dense central region. This crowded middle area is known as the galactic center. From our position in space, the galactic center lies in the direction of the constellation Sagittarius. If you were able to travel there, you would find a region where stars are packed far more closely together than they are in our part of the galaxy. But the galactic center is very far away from Earth. Astronomers estimate that our solar system sits about 26,000 light years from this central region. In other words, light traveling from the center of the Milky Way must journey across 26,000 years of space before reaching Earth. This idea can be surprising at first. When we observe the galactic center through telescopes, the light that reaches our eyes tonight actually began its journey long ago. The light left that region of space 26,000 years in the past and has been traveling toward us ever since. To understand what that means, it can help to compare that time span with human history. 26,000 years ago, humans had not yet built cities or written languages. Agriculture had not yet developed. Most human communities lived as small groups of hunter-gatherers, moving across landscapes in search of food. The pyramids of Egypt would not be built for another 20,000 years. Ancient civilizations such as Rome, Greece, and China still lay far in the future. Yet during all that time, the light from the center of our galaxy was already traveling toward Earth. Only now is that light finally arriving. This example helps illustrate the enormous scale of our galaxy. Even a single journey from the center of the Milky Way to our solar system takes tens of thousands of years for light to complete. And remember, light is the fastest thing known in the universe. Nothing can travel faster than light through empty space. Even the most advanced spacecraft humans have built travel vastly slower than this cosmic speed limit. For example, the fastest spacecraft ever launched from Earth move at speeds of only a few tens of kilometers per second. That may sound impressive, but compared to the speed of light, it is extremely slow. At those speeds, reaching the center of our galaxy would take far longer than 26,000 years. In fact, it would take many millions of years. This comparison helps show why astronomers rely on light itself when measuring cosmic distances. Light can cross the vast spaces between stars much faster than anything humans can currently build. But the galactic center is not just an empty region of space filled with stars. Astronomers have discovered that the very center of the Milky Way contains something even more extraordinary: a supermassive black hole. This black hole is known as Sagittarius A*, often pronounced Sagittarius A*. It contains millions of times the mass of our Sun and sits at the heart of the galaxy, surrounded by thousands of tightly packed stars. Scientists cannot see the black hole directly, but they can observe the motion of stars orbiting around it. By carefully tracking these stellar orbits, astronomers were able to determine the black hole's presence and measure its mass. Despite its enormous mass, Sagittarius A* does not control the entire galaxy by itself. Instead, the gravity of billions of stars and large amounts of unseen matter work together to hold the Milky Way together. Our solar system is simply one small part of this vast structure. We orbit the galaxy's center slowly, traveling along with billions of other stars in a long journey that takes hundreds of millions of years to complete. The distance between our solar system and the galactic center is just one small piece of the larger puzzle. Because the Milky Way extends both inward toward the center and outward toward distant regions of the disk, the total size of the galaxy must be much larger than this single measurement. Understanding how far we are from the center gives astronomers an important reference point. From that starting point, scientists can begin mapping the rest of the galaxy and estimating how far its spiral arms and outer regions stretch into space. And once we start looking beyond our own position in the Milky Way, the scale of the galaxy begins to grow far larger than most people imagine. Now that we know how far we are from the center of the Milky Way, we can begin to understand where our solar system fits inside the galaxy. The Milky Way is not shaped like a sphere. Instead, it is a spiral galaxy, meaning most of its stars are arranged in a wide, rotating disk, with curved arms that extend outward from the center. If you could somehow travel far outside the Milky Way and look back at it from a distance, you would likely see something similar to other spiral galaxies astronomers observe across the universe. The galaxy would appear as a glowing disk of stars, with graceful spiral arms winding outward from a bright central region. Our solar system is located somewhere within that disk, but we are not located in the middle of the galaxy. Instead, our Sun sits in a quieter region of one of the galaxy's spiral arms. This region is sometimes called the Orion Arm or the Orion Spur. The Orion Arm is not one of the largest spiral arms in the Milky Way. It is more like a smaller branch that sits between two much larger arms, known as the Perseus arm and the Sagittarius arm. Within this branch of the galaxy lies our solar system, moving slowly through space along with many other nearby stars. When astronomers look at the Milky Way, they often describe our position as being about halfway between the galactic center and the outer edge of the galaxy. We are not deep inside the crowded central bulge where stars are packed closely together. We are also not near the very edge where stars become more sparse. Instead, we occupy a middle region of the galactic disk. This location is actually quite fortunate for life on Earth. The central region of the Milky Way contains far more stars than our local neighborhood. With so many stars packed closely together, there would likely be much stronger radiation and more gravitational disturbances. Stars passing close to each other could potentially disrupt planetary systems. Out here in the Orion Arm, the environment is calmer. Stars are spaced much farther apart, which means our solar system has remained relatively stable for billions of years. This stability may have played an important role in allowing life to develop on Earth. Even though the distances between stars are enormous, the Milky Way still contains an incredible number of them. Astronomers estimate that there may be between 100 billion and 400 billion stars in our galaxy. Many of these stars have their own planets, forming countless solar systems spread across the Milky Way. Our Sun is simply one star among these vast numbers. Yet despite being only one star in such a huge galaxy, our solar system is not standing still. Like all stars in the Milky Way, the Sun is orbiting the center of the galaxy. Gravity from the combined mass of the galaxy keeps stars moving along curved paths around the galactic center. Our solar system travels through the Milky Way at a speed of about 220 kilometers per second. That may sound incredibly fast, but the distance around the galaxy is so large that completing one full orbit takes a very long time. In fact, the Sun needs roughly 225 to 250 million years to make one complete journey around the galaxy. Astronomers sometimes call this a galactic year. To put that in perspective, the dinosaurs first appeared on Earth about 1 galactic year ago. Since that time, our solar system has completed roughly one full orbit around the Milky Way. During all of human history, our solar system has only traveled a tiny fraction of that long path around the galaxy. As the Sun moves along its orbit, it carries the entire solar system with it. Earth, along with the other planets, travels through space as part of this larger galactic journey. Even while we stand still on the ground, our planet is moving through the galaxy at incredible speed. Understanding where we are in the Milky Way helps give us a sense of perspective. We are not at the center of the galaxy. We are not in a special or central location. Instead, we occupy a small, ordinary region within one spiral arm of a vast stellar system. But even though our position may seem modest, it gives us an excellent vantage point for studying the rest of the galaxy. From here, astronomers can observe the stars around us and gradually map the larger structure of the Milky Way. And when scientists began studying these patterns of stars, they started to uncover the larger shape of the galaxy itself. If you wanted to learn the shape of a distant object in space, the easiest way would usually be to step back and take a picture of it. Astronomers do this all the time with other galaxies. modern telescopes can capture beautiful images of spiral galaxies millions of light years away. In those pictures, the full structure of the galaxy is clearly visible. You can see the spiral arms, the bright center, and the outer edges of the disk all at once. But the Milky Way presents a special challenge. Unlike those distant galaxies, we are not observing the Milky Way from the outside. We are located inside it. Our solar system sits within the galaxy's disk, surrounded by billions of other stars. Because of this, we cannot simply move far enough away to photograph the entire galaxy from above. Instead, astronomers must study the Milky Way from within it, looking outward in every direction and slowly piecing together its structure. This situation can be compared to trying to map a forest while standing among the trees. If you walk through a dense forest, you can clearly see the trees around you. You may even see hundreds of them in every direction. But understanding the full shape of the forest, how wide it is, where it begins, and where it ends, is much harder. The trees themselves block your view, and the landscape stretches far beyond what you can easily observe from one location. Astronomers face a similar problem when studying the Milky Way. From Earth, we can observe nearby stars with great detail. We can also see distant stars scattered across the sky. But because we are inside the galaxy, our view is limited. We cannot see the entire structure at once. Early astronomers had an especially difficult time with this challenge. Before the invention of powerful telescopes, the night sky appeared mostly as a collection of individual stars. Some regions looked brighter than others, but the larger structure of the Milky Way remained mysterious. Scientists could only observe a small portion of the galaxy at a time. As telescopes improved, astronomers began to notice patterns. They realized that stars were not distributed evenly across the sky. Instead, they seemed to cluster along a wide band that stretched across the heavens. This band appeared brighter because it contained far more stars than other parts of the sky. But even with better instruments, much of the galaxy remained hidden. One of the biggest obstacles to observing the Milky Way is interstellar dust. This dust consists of tiny particles floating between the stars. Although these particles are extremely small, they can still block and scatter light traveling across space. When light from distant stars passes through thick clouds of dust, it can become dimmed or completely hidden from view. As a result, some parts of the galaxy are very difficult to observe using ordinary visible light. For many years, astronomers believed the Milky Way was smaller than it truly is, because these dust clouds prevented them from seeing distant regions of the galaxy. It was only later, when scientists developed new types of telescopes, that they began to overcome this problem. Infrared telescopes, for example, can detect longer wavelengths of light that pass more easily through dust clouds. Radio telescopes can also observe signals that travel through these dusty regions. By using these tools, astronomers were able to study parts of the Milky Way that had previously been hidden. Slowly, piece by piece, scientists began building a more complete map of our galaxy. They measured distances to nearby stars, tracked the movement of stellar clusters, and studied the distribution of gas and dust throughout the galaxy. Over time, these observations revealed that the Milky Way is a vast spiral system, with a central bulge and multiple curved arms extending outward. But long before astronomers understood these details, people had already noticed one of the galaxy's most recognizable features. Even without telescopes, the Milky Way reveals itself in a familiar and beautiful way. On very dark nights, far from city lights, a soft glowing band can be seen stretching across the sky. This glowing band is the combined light of billions of distant stars, and it provides our first visible clue about the true shape of the galaxy we live in. Long before telescopes were invented, people around the world noticed something unusual about the night sky. On the darkest nights, far away from bright city lights, a faint glowing band could be seen stretching across the heavens. This soft ribbon of light runs from one side of the sky to the other. It looks almost like a pale cloud, or a thin trail of mist drifting through the stars. Today we call this glowing band the Milky Way. For thousands of years, different cultures created stories to explain what they were seeing. In ancient Greece, the band of light was said to be milk spilled across the sky by the goddess Hera. In other cultures, it was described as a road, a river, or even a path followed by spirits. Although these stories were imaginative, they were all attempts to explain the same mysterious feature of the night sky. At first, people could only see this band with the naked eye. It appeared as a smooth glow without clear details. But when telescopes were invented in the early 1600s, astronomers began to look more closely. One of the first people to do this was Galileo Galilei. When Galileo pointed his telescope toward the Milky Way, he discovered something remarkable. The pale glow was not a cloud at all. Instead, it was made of an enormous number of stars, packed so closely together that they blended into a single band of light. What appeared to be a mist was actually the combined glow of countless distant suns. This discovery helped scientists realize that the Milky Way was not simply a decorative feature of the night sky. It was a vast system of stars that our own sun was part of. But why does the Milky Way appear as a band instead of filling the entire sky evenly? The answer has to do with the shape of our galaxy. As astronomers later discovered, the Milky Way is shaped like a wide, flattened disk. Most of the galaxy's stars lie within this disk, orbiting around the galactic center. Because the disk is relatively thin compared to its width, the stars are concentrated along a flat plane. Our solar system sits inside this disk. When we look up into the night sky, we are looking outward in every direction from within the galaxy. If we look above or below the disk, we see relatively fewer stars, because there are not as many stars in those directions. But when we look along the plane of the disk, our line of sight passes through huge numbers of stars. Imagine standing inside a long hallway filled with lights. If you look straight down the hallway, you can see many lights stretching into the distance. But if you turn and look at the wall beside you, you will only see a few lights nearby. Something similar happens when we observe the Milky Way. When we look along the disk of the galaxy, our view passes through billions of stars. Their combined light creates the glowing band that stretches across the sky. This band marks the direction where the galaxy's disk lies. The brightness of the band also changes depending on where you look. Some sections appear brighter and thicker than others. These brighter regions often point toward areas where stars are more densely packed, especially toward the center of the galaxy. Other regions appear darker. These dark patches are often caused by large clouds of interstellar dust, blocking the light from stars behind them. Even today, the Milky Way remains one of the most beautiful sights visible from Earth. On a clear night in a dark location, the band of light can be seen arching across the entire sky. For many people, seeing the Milky Way for the first time can be surprising. Modern cities are often so bright that this feature of the sky becomes invisible. Only when the sky is truly dark does the full glow of the galaxy become visible. This simple observation, just looking at the sky, already tells us something important about the structure of the Milky Way. The fact that the stars form a band instead of spreading evenly across the sky suggests that they are arranged in a flat system rather than a sphere. In other words, the night sky itself contains clues about the shape of the galaxy we live in. As astronomers continued studying the stars along this glowing band, they began noticing patterns in how the stars were arranged. These patterns eventually revealed that the Milky Way is not just a flat disk of stars. It also contains large curved structures known as spiral arms. And these spiral arms form the next important piece of the Milky Way structure. When astronomers first realized that the Milky Way was a flattened system of stars, they still did not fully understand what that system looked like. From Earth, we are stuck inside the galaxy. That means we cannot simply step outside and take a photograph of it from above. Instead, scientists had to slowly piece together its structure using careful observations. Over time, a clearer picture began to emerge. The Milky Way is not just a smooth disk filled evenly with stars. Instead, many of those stars are arranged into large curved patterns that wind outward from the center of the galaxy. These patterns are known as spiral arms. If you could view the Milky Way from far above, it would look something like a giant cosmic pinwheel. Several enormous arms would be seen spiraling outward from a bright central region, each filled with stars, gas, and dust. These arms are some of the most important structures in our galaxy. One reason they stand out so clearly is that spiral arms are regions where new stars are constantly forming. Inside the galaxy are vast clouds of gas and dust, known as molecular clouds. These clouds can collapse under their own gravity, forming new stars. Spiral arms tend to contain many of these clouds, making them active regions of starbirth. Because many young stars are extremely bright, spiral arms often shine more strongly than other parts of the galaxy. Young stars are typically larger, hotter, and more luminous than older stars. Their light helps highlight the curved shapes of the spiral arms when astronomers observe distant galaxies. But something interesting happens when scientists study how spiral arms behave. The stars inside them are not permanently attached to the arms themselves. Instead, stars slowly move in and out of spiral arms as they orbit the galaxy. To understand this, it helps to imagine a traffic jam on a busy highway. In a traffic jam, the slowdown itself can move along the road, even though individual cars are constantly entering and leaving the crowded area. The traffic jam is more like a pattern than a permanent group of specific cars. Spiral arms behave in a similar way. They are often described as density waves moving through the disk of the galaxy. As gas and stars travel through these regions of higher density, the gas can compress and trigger the formation of new stars. Once those stars form, they continue orbiting the galaxy, gradually drifting away from the spiral arm where they were born. This means the spiral arms are constantly being refreshed with new stars. The Milky Way is believed to contain several major spiral arms. Among the most well-known are the Perseus arm, the Sagittarius arm, the Scutum Centaurus arm, and the Norma arm. There are also smaller structures between these major arms called spurs or minor arms. Our solar system happens to sit within one of these smaller structures. The region we live in is called the Orion Arm, sometimes referred to as the Orion Spur. It lies between the larger Sagittarius and Perseus spiral arms. Although it is smaller than the main arms, it still contains many stars, nebulae, and stellar clusters. From our location inside the Orion Arm, the spiral structure of the Milky Way is difficult to see directly. Large clouds of dust block our view across much of the galaxy, especially toward the center. Because visible light cannot easily pass through these dense dust clouds, astronomers have had to rely on other methods to map the galaxy's structure. Radio waves and infrared light can travel through dust much more easily than visible light. Using radio telescopes and infrared observatories, scientists have been able to trace the locations of gas clouds and star-forming regions across the galaxy. By mapping these regions, they gradually revealed the shape of the Milky Way's spiral arms. Today, astronomers believe the Milky Way contains 4 major spiral arms, along with several smaller branches and spurs. Each of these arms stretches tens of thousands of light years across the galaxy. The spiral structure also plays an important role in shaping the environments where stars and planets form. Many of the most active star-forming regions in the galaxy are found along these curved arms. Massive nebulae, glowing clusters of newborn stars, and powerful stellar winds all contribute to the constantly changing landscape of the spiral arms. Although our solar system is currently located in a quieter region of the Orion Arm, it still shares the galaxy with these vast star-forming structures. Every star we see in the night sky, including our Sun, is part of this enormous rotating spiral system. And while the spiral arms define much of the Milky Way's visible structure, they are only one part of the galaxy. At the very center of the Milky Way lies a region far denser, brighter, and more mysterious than anything found in the spiral arms. If you follow the glowing band of the Milky Way across the night sky, one region appears brighter and thicker than the rest. This area lies in the direction of the constellation Sagittarius, and it marks the direction of the center of our galaxy. The galactic center is one of the most fascinating and mysterious places in the Milky Way. It is located about 26,000 light years away from Earth, deep within the crowded heart of the galaxy. From our perspective, it is hidden behind enormous clouds of dust and gas. These clouds block most visible light, which is why the galactic center does not appear as a brilliant point in the sky, despite containing a huge concentration of stars. For centuries, astronomers could not see what was actually there. Only in the 20th century did scientists begin using radio waves, infrared light, and X-rays to study the region beyond the dust. These forms of light can travel through the dense clouds that obscure the center in visible wavelengths. As these observations improved, astronomers discovered that the center of the Milky Way is an incredibly crowded environment. The region contains millions of stars packed into a relatively small volume of space. Star clusters sit close together, and powerful bursts of energy emerge from gas clouds that are constantly being heated and compressed. Compared with our quiet location in the Orion Arm, the galactic center is a far more extreme place. One of the most remarkable discoveries about the galactic center came from careful measurements of how stars move in this region. Astronomers noticed that many stars orbit around an invisible point in space at extremely high speeds. Some stars complete their orbits in just a few years, traveling at thousands of kilometers per second. Such rapid motion suggested that an enormous amount of mass must be concentrated at the very center. But the strange part was that no ordinary cluster of stars could account for the gravitational pull required to produce those speeds. The best explanation was something far more unusual. At the center of the Milky Way sits a supermassive black hole. This object is known as Sagittarius A star, pronounced Sagittarius A star. It contains roughly 4 million times the mass of our Sun, compressed into a region far smaller than our solar system. A black hole forms when matter becomes so densely packed that its gravity prevents even light from escaping. Once something crosses the boundary around a black hole, called the event horizon, it cannot return. Although black holes themselves emit no light, astronomers can detect them indirectly by studying how nearby stars and gas behave. The stars orbiting Sagittarius A star follow paths that reveal the presence of a massive, invisible object at the center of their motion. These observations provide some of the strongest evidence that the Milky Way contains a supermassive black hole. Despite its enormous mass, Sagittarius A star does not currently consume large amounts of material. In some galaxies, supermassive black holes are extremely active. They pull in large quantities of gas and dust, which heat up and release intense radiation as they spiral inward. These active galactic centers can outshine the entire galaxy around them. The Milky Way's black hole, however, is relatively quiet. Most of the time it sits in a low activity state, occasionally swallowing small amounts of gas that drift too close. When this happens, brief bursts of energy can be detected in X-rays or radio waves. Even though the black hole dominates the gravitational center of the galaxy, its influence fades quickly with distance. At the scale of the entire Milky Way, the motion of stars is determined mainly by the combined gravity of hundreds of billions of stars, along with vast quantities of gas, dust, and dark matter. Our solar system, for example, orbits the center of the galaxy far beyond the region where the black hole's gravity directly dominates. In fact, the Sun takes about 225 to 250 million years to complete one full orbit around the galactic center. This enormous journey is sometimes called a galactic year. During that time, the Sun and its planets travel through different regions of the Milky Way's spiral structure. Although the galactic center is far away and hidden from direct view, it still plays a crucial role in shaping the overall structure of the galaxy. The immense mass at the center helps anchor the rotating disk of stars that extends tens of thousands of light years outward. But even the galactic center is not the full story of the Milky Way. Beyond the spiral arms and far outside the bright disk of stars lies a much larger and more mysterious component of the galaxy, one that extends far beyond what we can easily see. This outer region forms a vast spherical envelope surrounding the Milky Way. When most people imagine the Milky Way, they picture the bright spiral disk filled with stars and glowing clouds of gas. This disk, along with its spiral arms, is certainly the most visible part of our galaxy. But the Milky Way does not end at the edge of its spiral arms. Far beyond the thin disk lies a much larger and more diffuse region known as the galactic halo. The halo forms a vast spherical envelope surrounding the entire galaxy. While the disk stretches roughly 100,000 light-years across, the halo extends far beyond that, reaching perhaps several 100,000 light-years into space. Compared to the crowded spiral arms, the halo is extremely sparse. stars in the halo are spread very far apart, and the region contains far less gas and dust than the disk. Because of this, the halo is much harder to observe. It does not glow brightly like the Milky Way band we see in the night sky. Yet it still plays an important role in the structure of the galaxy. One of the most noticeable features of the halo is the presence of globular clusters. Globular clusters are dense spherical groups of stars that orbit the galaxy far above and below the galactic disk. Each cluster can contain hundreds of thousands or even millions of stars tightly bound together by gravity. These clusters are among the oldest objects in the Milky Way. Many globular cluster stars formed more than 12 billion years ago, not long after the galaxy itself began to take shape. Because of their great age, studying these clusters helps astronomers learn about the early history of the Milky Way. Unlike stars in the disk, which move in relatively flat circular paths around the galactic center, globular clusters follow much more varied orbits. Some plunge through the galactic disk before rising far above it again. Others travel along wide, elongated paths that carry them deep into the halo. Their movements reveal that the halo is not organized like the rotating disk of the galaxy. Instead, objects in the halo move in many different directions, creating a much more chaotic structure. Another interesting difference between halo stars and disk stars involves their chemical composition. Stars in the galactic disk often contain heavier elements such as carbon, oxygen, silicon, and iron. These elements are created inside stars and spread into space when stars die in supernova explosions. Over billions of years, new generations of stars formed from this enriched material, gradually increasing the abundance of heavy elements in the galaxy. Halo stars, however, often contain far fewer heavy elements. This suggests that they formed very early in the galaxy's history, before many cycles of star formation had taken place. In a sense, halo stars act as ancient fossils from the early universe. Beyond the visible stars and globular clusters, the halo contains something even more mysterious. Astronomers have discovered that galaxies, including the Milky Way, are surrounded by enormous quantities of dark matter. Dark matter does not emit light, reflect light, or absorb light in ways that telescopes can detect. Yet its gravitational effects can be measured by observing how stars and gas move within galaxies. When scientists studied the rotation of galaxies, they found something surprising. Stars far from the center were orbiting much faster than expected. Based only on the visible matter in galaxies, these outer stars should move more slowly. Instead, their speed suggested that a huge amount of unseen mass must be present. This unseen mass appears to form a massive dark matter halo surrounding the visible galaxy. In the Milky Way, the dark matter halo likely contains several times more mass than all the stars combined. Although we cannot see dark matter directly, its gravity helps hold the galaxy together. Without it, the outer stars would not remain bound to the galaxy in the way we observe. The presence of dark matter also affects how galaxies form and evolve over cosmic time. Computer simulations suggest that galaxies like the Milky Way began forming within large clouds of dark matter. As gas cooled and collapsed within these dark matter halos, stars gradually formed, eventually creating the visible galaxy we see today. So while the spiral disk may be the most recognizable part of the Milky Way, it represents only a fraction of the galaxy's full structure. The halo extends far beyond the bright stars, containing ancient clusters scattered stars, and an enormous invisible framework of dark matter. Together, these components create a galaxy far larger and more complex than what we see in the night sky. And even within this vast system, our solar system occupies only a tiny and quiet corner of the galaxy's immense structure. With hundreds of billions of stars spread across a galaxy, more than 100,000 light-years wide, it can be difficult to picture exactly where we are within the Milky Way. The truth is that our solar system does not sit anywhere near the center of the galaxy. Instead, we live in a relatively quiet outer region of the galactic disk. Our position is about 26,000 light-years from the galactic center, placing us roughly halfway between the center of the Milky Way and its outer edge. This location turns out to be surprisingly comfortable. The center of the galaxy is a much more crowded and energetic place. Stars there are packed much closer together, and intense radiation from energetic events can make the environment far more chaotic. Our region, by contrast, is relatively calm. The Sun lies within a smaller structure known as the Orion Arm, sometimes called the Orion Spur. This is not one of the Milky Way's major spiral arms, but rather a smaller branch located between two larger arms, the Sagittarius Arm and the Perseus Arm. Although it is considered a minor structure, the Orion Arm still contains thousands of stars and many star-forming nebulae. Some of the most familiar stars in the night sky are actually located within this same region of the galaxy. Bright stars like Betelgeuse, Rigel, and many others belong to nearby stellar neighborhoods within the Orion Arm. From our position inside the disk, the stars around us appear scattered across the sky in every direction. But when astronomers measure the distances and motions of these stars, they find that they are all part of the same enormous rotating system. The Sun itself is not stationary within the Milky Way. It is constantly moving as it orbits the galaxy's center. In fact, our solar system travels at a speed of roughly 220 kilometers per second as it moves along its galactic orbit. At that speed, it still takes an incredibly long time to complete a single trip around the galaxy. One full orbit of the Sun around the Milky Way is called a galactic year, and it lasts about 225 to 250 million Earth years. This means that during the entire history of Earth, the Sun has completed only about 20 galactic orbits. When the dinosaurs first appeared on Earth, the solar system was located in a completely different part of the galaxy than it is today. While the Sun moves along this enormous path, it also drifts slightly above and below the galactic plane. The Milky Way's disk is not perfectly flat. Instead, stars oscillate gently up and down as they orbit the center. The Sun currently sits close to the middle of this disk, but over time, it slowly moves above and below it in a gradual wave-like motion. Each vertical oscillation takes tens of millions of years. Despite this constant motion, the distances between nearby stars remain enormous. Even the closest star system to us, Alpha Centauri, lies more than 4 light-years away. In most regions of the galaxy, stars are separated by similarly vast distances. This means that collisions between stars are extremely rare, even though the galaxy contains so many of them. Our position in the Milky Way also influences what we can see in the night sky. Because we are located within the galactic disk, our view across the galaxy is partially blocked by clouds of gas and dust. These interstellar clouds absorb and scatter visible light, hiding many distant stars from direct observation. This is one reason why mapping the full structure of the Milky Way has been such a difficult challenge for astronomers. In contrast, if we lived far above the disk of the galaxy, we would have a much clearer view of the Milky Way's spiral structure from the outside. From our current vantage point, however, we must study the galaxy from within, gradually building a picture of its structure using measurements of star distances, radio signals from gas clouds, and observations in infrared light. Even with these limitations, astronomers have been able to determine that the Milky Way is a vast rotating system with a complex structure of spiral arms, star clusters, and interstellar clouds. And within this enormous galaxy, our solar system occupies only a tiny region along one of its smaller spiral branches. But even though our location might seem ordinary, it places us in a stable environment where stars are widely spaced and catastrophic events are relatively rare. This quiet corner of the Milky Way may have played an important role in allowing life to develop on Earth. And as we continue exploring the galaxy, we are gradually discovering that the Milky Way is not alone in the universe. It is part of a much larger cosmic neighborhood filled with other galaxies. For most of human history, people had no way of knowing how large the Milky Way actually was. The glowing band in the night sky was visible to anyone who looked up on a dark night. But its true nature remained mysterious for thousands of years. Without telescopes or modern instruments, the Milky Way appeared simply as a faint river of light crossing the heavens. Many early thinkers assumed that this band of light contained all the stars that existed. In fact, some early astronomers believed the Milky Way might represent the entire universe. If every visible star belonged to this single structure, then perhaps the universe itself was simply a large collection of stars surrounding Earth. This idea persisted for a long time because measuring distances to stars was incredibly difficult. Even the closest stars are so far away that their distances cannot be measured in ordinary units, like kilometers or miles. Instead, astronomers eventually had to develop new methods that could estimate distances across the vast emptiness of space. The first important clues came in the late 19th and early 20th centuries, when telescopes became powerful enough to reveal far more stars than the naked eye could see. Through these improved telescopes, astronomers discovered that the Milky Way was filled with enormous numbers of faint stars that were invisible without magnification. This discovery suggested that the galaxy might be much larger than anyone had previously imagined. At the same time, scientists began developing ways to measure how far away some of these stars might be. The challenge was enormous. When we look at the night sky, stars appear scattered across a flat dome above us. Without additional information, it is almost impossible to tell which stars are nearby and which ones lie far deeper in space. Two stars may appear side by side in the sky, even though one is hundreds of times farther away than the other. Early astronomers therefore needed a way to determine the true three-dimensional structure of the Milky Way. During the early 1900s, researchers began collecting large amounts of observational data. They carefully measured the brightness of stars, recorded their positions in the sky, and compared observations made from different observatories around the world. Slowly, astronomers started assembling the first crude maps of star locations. These early maps did not yet reveal the spiral shape of the Milky Way, but they provided an important first step toward understanding its structure. One of the scientists who contributed significantly to these efforts was Jacobus Kapteyn, a Dutch astronomer who attempted to map the distribution of stars throughout the galaxy. Kapteyn analyzed the brightness and motion of thousands of stars, hoping to estimate their distances and positions. Using this data, he constructed one of the earliest models of the Milky Way. His model suggested that the galaxy was shaped somewhat like a flattened disk, with the Sun located near the center. Although we now know this part of the model was incorrect, the effort itself was a remarkable achievement for its time. Kapteyn and other astronomers were working with limited tools and incomplete data, yet they were beginning to uncover the true scale of the galaxy. The main difficulty was that interstellar dust blocked much of the light coming from distant stars. This dust made distant regions of the galaxy appear dimmer than they really were, causing early measurements to underestimate how far the Milky Way extended. Even with these limitations, the growing number of star measurements hinted that the galaxy was far larger than previously believed. Astronomers realized that if they could find reliable ways to measure star distances, they could begin constructing a far more accurate map of the Milky Way. That challenge soon led to the development of several powerful distance measuring techniques. The first of these techniques relied on a subtle shift in how nearby stars appear when viewed from different points in Earth's orbit. This method became one of the earliest reliable tools for measuring the distances to stars close to our solar system. It is known as stellar parallax. One of the first reliable ways astronomers learned to measure distances in space is a method called parallax. The idea behind parallax is surprisingly simple. It relies on the fact that an object can appear to shift slightly when viewed from two different positions. You may have noticed this effect in everyday life. If you hold your finger out in front of your face and look at it with one eye closed, then switch to the other eye, your finger seems to move slightly against the background. Your finger is not actually moving. The shift happens because each eye views the finger from a slightly different angle. Astronomers realized that a similar effect could be used to measure distances to nearby stars. Instead of using two eyes, however, they used two different positions of Earth in its orbit around the Sun. As Earth travels around the Sun once each year, our viewing position in space changes by about 300 million kilometers. 6 months after observing a star from one side of Earth's orbit, we are viewing it again from the opposite side. This shift provides two different viewing angles of the same star. If the star is relatively close to us, it will appear to move slightly against the background of much more distant stars. This tiny apparent motion is called stellar parallax. The amount of this shift is extremely small. Even the nearest stars move only a tiny fraction of a degree across the sky when measured using parallax. In fact, the shifts are usually measured in units called arcseconds, which divide a single degree into 3,600 smaller parts. For most stars, the shift is far smaller than 1 arcsecond. Because these angles are so tiny, measuring them accurately requires extremely precise instruments. The first successful measurement of stellar parallax was made in 1838 by Friedrich Bessel, a German astronomer. Bessel studied the star 61 Cygni, which was known to move relatively quickly across the sky. After carefully observing the star over time, Bessel detected a small parallax shift that revealed its distance from Earth. This measurement confirmed something important. Stars were not just distant lights fixed to the sky. They were incredibly far-away objects scattered through space. Using parallax measurements, astronomers could now determine distances to nearby stars with much greater confidence. To make these measurements easier to work with, scientists created a special unit of distance called the parsec. A parsec is defined as the distance at which a star would show a parallax shift of exactly 1 arc-second as Earth moves around the Sun. 1 parsec equals about 3.26 light-years. Although this unit might sound unusual, it allows astronomers to calculate distances directly from parallax measurements using simple geometry. As telescopes improved, astronomers measured the parallax of more and more nearby stars. This allowed them to build the first accurate maps of the solar neighborhood, showing the positions of stars located within a few dozen light-years of the Sun. These early measurements revealed that space is far emptier than people once imagined. Even the closest stars are separated by enormous distances. For example, the nearest star system beyond our own, Alpha Centauri, lies about 4.37 light-years away. In other words, light from that system takes more than 4 years to reach Earth. While parallax is extremely useful, it has an important limitation. Because the shifts are so tiny, the method only works well for stars that are relatively close to Earth. For stars located farther away, the parallax angle becomes too small to measure accurately. For many years, parallax measurements could only reach distances of a few hundred light-years. Modern space telescopes have extended this range significantly. Missions such as the Gaia spacecraft have measured the positions and motions of more than 1 billion stars, allowing astronomers to determine distances across large portions of the Milky Way. Even so, parallax alone cannot measure the distances to stars on the far side of the galaxy. To map the entire Milky Way, astronomers needed another way to measure much greater distances. Fortunately, the universe provides certain stars whose behavior reveals their true brightness. By studying these special stars, scientists discovered a powerful new method for measuring distances far across the galaxy. As astronomers began measuring distances to nearby stars using parallax, they quickly ran into a major limitation. Parallax works very well for stars that are relatively close to Earth. But the farther away a star is, the smaller its apparent shift becomes as Earth moves around the Sun. Eventually, the shift becomes so tiny that it is nearly impossible to measure accurately. This meant that parallax alone could not map the entire Milky Way. If astronomers wanted to measure distances across the galaxy, they needed another method, one that could work over much larger scales. The breakthrough came from studying a special type of star known as a variable star. Most stars shine with a fairly steady brightness over long periods of time, but some stars behave very differently. Instead of remaining constant, their brightness changes in a regular pattern. These stars brighten and dim over time, sometimes completing a full cycle in just a few days or weeks. One particular group of variable stars became especially important to astronomers. These are known as Cepheid variable stars. Cepheid variables are large, luminous stars that repeatedly expand and contract. As the star expands, its outer layers cool slightly, and its brightness changes. When the star contracts again, its temperature and brightness increase. This rhythmic pulsing causes the star's light to vary, in a predictable cycle. The key discovery about Cepheid variables came in the early 20th century through the work of Henrietta Swan Leavitt, an astronomer studying stars in the Small Magellanic Cloud. While examining photographic plates of the sky, Leavitt noticed something remarkable. Cepheid variable stars did not all brighten and dim at the same speed. Some completed their cycles quickly, while others took longer. When Leavitt carefully compared their behavior, she found a pattern. Cepheids with longer pulsation periods were also intrinsically brighter than those with shorter periods. In other words, the time it took for a Cepheid to complete its brightness cycle revealed how bright the star truly was. This relationship became known as the period luminosity relation. The discovery was extremely powerful because it allowed astronomers to determine the true brightness of a Cepheid variable simply by measuring how long its brightness cycle lasted. Once the true brightness of a star is known, determining its distance becomes much easier. This works because light becomes dimmer as it travels through space. A bright object far away can appear just as faint as a dim object nearby. But if astronomers know how bright the object truly is, they can compare that to how bright it appears from Earth. The difference between the true brightness and the observed brightness reveals the distance to the star. Cepheid variable stars therefore became an incredibly valuable tool for measuring distances across the Milky Way. Unlike Parallax, which only works for nearby stars, Cepheid variables can be observed at much greater distances because they are extremely luminous. Some Cepheids are thousands of times brighter than our Sun, making them visible across large portions of the galaxy. Using Cepheid variables as distance markers, astronomers began mapping stars much farther away than ever before. One of the scientists who used this technique to transform our understanding of the galaxy was Harlow Shapley. Shapley studied Cepheid variables located within globular clusters, those dense groups of ancient stars that orbit far above and below the galactic disk. By measuring the brightness cycles of Cepheid stars within these clusters, Shapley estimated their distances from Earth. What he discovered was surprising. Many globular clusters were located extremely far away, far beyond the region where earlier astronomers believed the Milky Way ended. Even more interesting was the pattern of where these clusters appeared to be concentrated. Instead of surrounding the Sun evenly in all directions, the clusters seemed to gather in one particular region of the sky. This region pointed toward the constellation Sagittarius. From this pattern, Shapley concluded that the center of the Milky Way must lie in that direction, far away from our solar system. His work helped reveal two important truths about our galaxy. First, the Milky Way was far larger than previously believed. Second, the Sun was not located at the center of the galaxy. Instead, our solar system occupies a position far out in the galaxy's disk. By combining parallax measurements for nearby stars with Cepheid variable measurements for distant stars, astronomers finally began to understand the enormous scale of the Milky Way. These techniques allowed scientists to measure distances across thousands and even tens of thousands of light years. But understanding the galaxy's size required more than just measuring distances. Astronomers also needed to study how stars move within the galaxy itself. Those motions provided another powerful clue about the true structure of the Milky Way. By the early 20th century, astronomers had begun to measure the distances to many stars across the Milky Way. Techniques such as Parallax and Cepheid variable stars, provided new tools for mapping the galaxy's structure. But distance alone could not reveal everything about the Milky Way. Scientists also wanted to understand how the galaxy moves. If the Milky Way is a massive system of stars, gas, and dust, then those objects must be influenced by gravity. Just as the planets orbit the Sun, stars should move through the galaxy in organized patterns, shaped by the galaxy's mass. By studying these motions, astronomers could learn much more about the structure and size of the Milky Way. One of the first important clues came from measuring how stars move through space. Stars do not remain fixed in the sky. Over long periods of time, they slowly change position relative to one another. These motions are extremely gradual, so they are difficult to notice without precise measurements made over many years. Astronomers track these movements using two main methods. The first method measures proper motion, which is the slow sideways movement of a star across the sky when observed over long periods. The second method measures radial velocity, which describes how fast a star is moving toward or away from us. This is detected using the Doppler effect, where the light from a star shifts slightly toward red or blue wavelengths, depending on its motion. By combining these measurements, astronomers can determine the full three-dimensional motion of many stars. When scientists began analyzing the motion of large numbers of stars, a clear pattern started to appear. Most stars in the Milky Way are orbiting around the galactic center. This motion is somewhat similar to the way planets orbit the Sun, although the scales involved are far larger. Instead of a few planets circling a star, hundreds of billions of stars are slowly orbiting the center of the galaxy. Our own Sun is part of this motion. The solar system travels around the center of the Milky Way at a speed of roughly 220 kilometers per second. Even at that enormous speed, the distance is so large that it takes about 225 to 250 million years to complete one full orbit. That means Earth has only completed about 20 such orbits since it first formed. Astronomers soon realized that measuring how fast stars move at different distances from the galactic center could reveal the distribution of mass within the galaxy. If most of the galaxy's mass were concentrated near the center, then stars farther out should orbit more slowly, just as the outer planets in our solar system move more slowly than the inner planets. But when scientists measured the speeds of stars across the galaxy, they discovered something unexpected. Stars far from the center were not slowing down as much as predicted. Instead, many outer stars were moving almost as fast as those located closer to the center. This pattern appeared repeatedly when astronomers studied the rotation of galaxies. The results were plotted on graphs known as galactic rotation curves. Rather than showing a steady decline in speed with distance, the curves tended to remain relatively flat. This meant that stars far from the center were moving faster than expected based on the visible matter alone. This observation suggested that the Milky Way must contain much more mass than we can see. The extra mass could not be explained by stars, gas, or dust. Instead, astronomers concluded that the galaxy must be surrounded by a vast amount of unseen material. This mysterious substance became known as dark matter. Dark matter does not emit light and cannot be directly observed with telescopes. However, its gravitational influence can be detected through the motions of stars and galaxies. In the Milky Way, dark matter appears to form a large halo surrounding the visible galaxy. Its gravity helps keep stars moving at the speeds we observe. Studying the rotation of the galaxy also helped astronomers estimate its overall size. By analyzing the motion of stars and gas clouds across large distances, scientists could infer how far the galaxy extends and how much mass it contains. These measurements showed that the Milky Way is not just a cluster of nearby stars. It is an enormous rotating system stretching tens of thousands of light-years across. Combining motion measurements with distance measuring techniques finally allowed astronomers to begin estimating the true scale of the galaxy. And once those estimates became clearer, scientists realized that the Milky Way was far larger than anyone had previously imagined. After decades of studying star distances, variable stars, and the motion of stars across the galaxy, astronomers slowly began to piece together a clearer picture of the Milky Way's true size. The result was astonishing. The galaxy we live in is far larger than early astronomers ever imagined. Today, most scientific estimates place the diameter of the Milky Way's stellar disk at roughly 100,000 light-years. This means that if a beam of light started on one side of the galaxy and traveled straight across to the other side, it would take about 100,000 years to make the journey. To understand just how vast that distance is, it helps to compare it to something closer to home. Light travels extremely fast, moving at about 300,000 kilometers per second. At that speed, light can circle the Earth more than 7 times in a single second. Yet even traveling this quickly, light still needs more than 100,000 years to cross the Milky Way. This gives us a sense of the enormous scale of our galaxy. Within this disk of stars lie hundreds of billions of individual stars, along with vast clouds of gas and dust, where new stars are constantly forming. The disk itself is where most of the visible matter in the Milky Way is concentrated. When we see the glowing band of the Milky Way stretching across the night sky, we are looking through this dense disk of stars. The galaxy's diameter refers primarily to this region. However, measuring the exact size of the Milky Way is not perfectly straightforward. One reason is that the edges of the galaxy are not sharply defined. Instead, the density of stars gradually decreases as you move farther away from the center. In other words, there is no clear boundary where the galaxy suddenly ends. Some stars exist well beyond the main disk, and faint stellar streams can extend even farther into space. Because of this, different measurements can produce slightly different estimates of the galaxy's total size. Some studies suggest that the visible disk might extend a little farther than 100,000 light-years, possibly reaching 120,000 light-years or more. But regardless of the exact number, the Milky Way remains an enormous structure by any standard. Even the distance from our solar system to the galactic center is immense. At about 26,000 light-years away, the center of the Milky Way lies roughly halfway across the galaxy from our position. That means the Sun sits comfortably within the disk, rather than near the outermost edge. If we could somehow travel at the speed of light, reaching the center of the galaxy would still require 26,000 years of continuous travel. Of course, no spacecraft can travel anywhere close to the speed of light with current technology. At the speeds achieved by modern spacecraft, crossing the Milky Way would take far longer than the entire history of human civilization. Even our fastest probes would require tens of millions of years to travel comparable distances. Another way astronomers estimate the size of the galaxy involves studying the distribution of gas clouds and star-forming regions within the Milky Way. These clouds, often detected through radio observations, reveal where large concentrations of matter exist within the galactic disk. By mapping these regions across the sky, astronomers can trace the structure of the galaxy and estimate how far its spiral arms extend. Observations of distant stars and star clusters also help confirm these measurements. Some stars are found far from the center, but still clearly belong to the Milky Way's rotating disk. Together, these observations provide strong evidence that the galaxy's disk stretches tens of thousands of light-years in every direction. Yet while the diameter of the Milky Way tells us how wide the galaxy is, it does not describe the full shape of the galaxy. The Milky Way is not a sphere like a star or a planet. Instead, it is much thinner than it is wide. When astronomers began studying the vertical structure of the galaxy, they discovered that most stars are confined to a relatively narrow layer. In other words, the Milky Way resembles a flattened disk rather than a round ball of stars. Understanding the thickness of that disk reveals another important piece of the galaxy's structure. When people first learned that the Milky Way is about 100,000 light-years across, it is natural to imagine the galaxy as something like a giant sphere of stars. But in reality, the Milky Way has a very different shape. Instead of being round, the galaxy is extremely flat compared to its width. Most of the stars in the Milky Way are concentrated in a relatively thin layer that forms the galaxy's disk. This disk is where the spiral arms exist, where new stars are born, and where most of the gas and dust in the galaxy can be found. While the Milky Way stretches roughly 100,000 light-years from side to side, the thickness of the main stellar disk is only about 1,000 light-years. That means the galaxy is about 100 times wider than it is thick. To picture this shape, imagine a glowing cosmic pancake or a thin spinning record made of stars. If we could somehow travel far outside the Milky Way and view it from the side, we would see a bright, flattened disk with a slight bulge in the middle where the galactic center lies. The outer edges would appear thinner and more diffuse, gradually fading into the darkness of space. Within this disk lies the thin disk, which contains most of the galaxy's stars, including our Sun. The thin disk is where the spiral arms are located. It is also where most of the galaxy's gas and dust reside. These materials are essential for forming new stars, so the thin disk is where star formation happens most actively. Because of this, many young stars are found in the thin disk. Young stars tend to remain close to the galactic plane because they form within dense clouds of gas and dust that are concentrated in this region. But the Milky Way's vertical structure is a little more complicated than a single thin layer. Astronomers have discovered that there is also a thicker disk of stars surrounding the thin disk. This structure is known as the thick disk, and it extends several thousand light-years above and below the galactic plane. Stars in the thick disk are generally older than those in the thin disk. They also move differently. While thin disk stars orbit the galaxy in relatively flat paths close to the plane, thick disk stars follow orbits that carry them farther above and below the galactic disk. Their motions are somewhat more scattered and less tightly confined. The reason for this difference is still an area of active research. Some scientists believe the thick disk may have formed long ago when smaller galaxies collided with the early Milky Way. These collisions could have stirred up the motions of stars, causing them to move in more tilted orbits. Over billions of years, this would have created a thicker layer of stars surrounding the thin disk. Above and below the thick disk lies an even more extended region called the galactic halo, which we discussed earlier. Halo stars can travel thousands or even tens of thousands of light years away from the galactic plane. But compared to the dense disk of the galaxy, the halo contains far fewer stars. Another important feature of the Milky Way's vertical structure involves gas and dust. These materials are mostly concentrated in the thin disk, where gravity pulls them toward the galactic plane. Because of this, the thin disk contains the clouds of gas that eventually collapse to form new stars. These star-forming regions often appear as glowing nebulae scattered along the spiral arms. The concentration of gas and dust in the disk is also the reason why the Milky Way appears as a band of light in the night sky. When we look along the plane of the galaxy, our line of sight passes through enormous numbers of stars packed within this thin layer. But when we look above or below the galactic plane, we see far fewer stars because we are looking out of the disk and into the much emptier halo. This structure gives the Milky Way its familiar appearance as a glowing ribbon stretching across the sky. Understanding the thickness of the galaxy helps astronomers visualize the three-dimensional shape of the Milky Way. Instead of a uniform cloud of stars, the galaxy is a layered system with a thin disk, a thicker surrounding disk, and a vast halo extending far beyond both. Within the thin disk alone lie hundreds of billions of stars, each moving along its own path through the galaxy. And when we consider just how many stars exist within this relatively thin layer of space, the true scale of the Milky Way becomes even more remarkable. When people first learn about the size of the Milky Way, one question almost immediately follows. How many stars are actually inside our galaxy? The answer is surprisingly difficult to determine. Astronomers currently estimate that the Milky Way contains somewhere between 100 billion and 400 billion stars. That range may sound enormous, but the uncertainty exists for a good reason. Counting the stars in a galaxy is far more complicated than simply pointing a telescope at the sky. For one thing, many stars are extremely faint. Large, bright stars like our Sun are relatively easy to detect, even from great distances. But the majority of stars in the Milky Way are much smaller and dimmer. These stars, known as red dwarfs, emit far less light and are therefore much harder to see across long distances. In fact, red dwarfs may make up the majority of all stars in the galaxy. Because they are so faint, many of them can only be detected when they are relatively close to Earth. Detecting similar stars on the far side of the Milky Way is extremely difficult. Another major challenge comes from the dust clouds scattered throughout the galaxy. As we discussed earlier, the Milky Way's disk contains large quantities of gas and dust. These clouds absorb and scatter visible light, blocking our view of many distant stars. In some directions, especially toward the center of the galaxy, this dust can obscure enormous regions of space. That means there may be vast numbers of stars hidden behind these dusty regions that telescopes cannot easily see. Astronomers try to overcome this limitation by observing the galaxy in infrared and radio wavelengths, which can pass through dust much more easily than visible light. These observations help reveal stars and gas clouds that would otherwise remain hidden. Even with these advanced techniques, however, measuring the total number of stars directly remains nearly impossible. Instead, astronomers estimate the number using statistical methods. One approach involves studying a small region of the galaxy in detail and counting how many stars appear within that area. Scientists then estimate how many similar regions exist throughout the galaxy and use those numbers to calculate a total. Another method uses measurements of the galaxy's total mass. By studying how stars and gas move within the Milky Way, astronomers can estimate the galaxy's overall mass. From there, they can approximate how many stars would be needed to account for that mass, along with contributions from gas, dust, and dark matter. These methods do not produce an exact count, but they give scientists a useful estimate of the galaxy's stellar population. What makes the Milky Way particularly impressive is not just the number of stars, but the variety of stars it contains. Some stars are young and bright, burning hot and blue as they rapidly consume their fuel. Others are older and cooler, glowing with reddish light as they slowly fade over billions of years. Many stars exist in pairs or groups known as binary systems, where two stars orbit around each other. Others belong to clusters containing thousands or even millions of stars packed closely together. Every one of these stars is part of the enormous rotating system that forms our galaxy. And each of those stars may also host its own planets. In recent years, astronomers have discovered that planets are extremely common throughout the galaxy. Observations suggest that many stars likely have planetary systems of their own. This means the Milky Way could contain hundreds of billions of planets, scattered among its hundreds of billions of stars. Despite these vast numbers, the stars in the galaxy are still separated by enormous distances. Even within the crowded disk of the Milky Way, stars are typically separated by several light years. Space remains mostly empty, with stars occupying only tiny points within an immense cosmic volume. Yet even with hundreds of billions of stars spread across the disk, the Milky Way does not end there. Beyond the bright spiral arms and the thin disk lies another region that extends much farther into space. This outer region contains far fewer stars, but it stretches well beyond the visible boundaries of the galaxy. Astronomers refer to this region as the stellar halo. When we picture the Milky Way, we usually imagine the bright disk of stars and spiral arms that form the glowing band across the night sky. This disk contains most of the stars we can easily observe, along with the gas and dust that create new generations of stars. But the Milky Way does not stop at the edge of this disk. Far beyond the spiral arms lies a much larger and more diffuse region, known as the stellar halo. The stellar halo surrounds the entire galaxy like a vast, nearly spherical envelope. It stretches far above and below the galactic disk, extending tens of thousands of light years into space. Unlike the disk, which is densely packed with stars, the halo contains far fewer stars spread across an enormous volume. If you could travel through the halo, the sky would look very different from what we see here on Earth. Instead of a crowded field of stars forming the bright Milky Way band, you would see long stretches of darkness with only occasional stars scattered across the sky. Despite its sparse appearance, the stellar halo is still an important part of the galaxy. Many of the stars in this region are extremely old. Astronomers believe that halo stars formed early in the history of the Milky Way, not long after the galaxy itself began to assemble. Because of their age, these stars contain fewer heavy elements than younger stars found in the disk. Elements such as carbon, oxygen, and iron are created inside stars and released into space when stars die in powerful explosions known as supernovae. Over billions of years, these explosions enrich the surrounding gas with heavier elements, allowing new generations of stars to form with more complex chemical compositions. But halo stars formed before many of these enrichment cycles occurred. As a result, they contain relatively small amounts of these heavier elements. Studying these ancient stars helps astronomers learn about the early conditions of the Milky Way and the universe itself. The halo is also home to many of the globular clusters that orbit the galaxy. Globular clusters are dense spherical collections of stars that can contain hundreds of thousands or even millions of stars packed closely together. Unlike open star clusters in the galactic disk, globular clusters are extremely old and stable systems. Many of them formed more than 12 billion years ago, making them some of the oldest known objects in the Milky Way. These clusters orbit the galaxy in wide, looping paths that often carry them far above and below the galactic plane. Some of their orbits even plunge through the disk before rising back into the halo again. Because globular clusters are bright and relatively easy to detect, astronomers have used their positions to help map the structure of the galaxy. Early in the 20th century, the distribution of globular clusters helped scientists identify the approximate direction of the galactic center. Instead of surrounding the Sun evenly, these clusters appeared concentrated toward one region of the sky, indicating that the center of the Milky Way lay far away in that direction. Another interesting feature of the stellar halo is the unusual motion of its stars. Stars in the galactic disk tend to orbit the center of the galaxy in relatively smooth circular paths. Halo stars, however, move in far more complex ways. Some travel along elongated orbits that carry them thousands of light years above and below the galactic plane. Others move at steep angles relative to the disk, creating a far more chaotic pattern of motion. These unusual orbits suggest that the halo formed through a different process than the disk. Many astronomers believe the halo contains the remains of smaller galaxies that were absorbed by the Milky Way long ago. Over billions of years, gravity gradually pulled these smaller galaxies apart, scattering their stars into wide orbits around the larger galaxy. Evidence of these ancient mergers can still be seen today. Astronomers have discovered faint stellar streams in the halo, long trails of stars that appear to be the remnants of dwarf galaxies torn apart by the Milky Way's gravity. These streams act like fossil records, preserving clues about the galaxy's past interactions. Although the stellar halo contains relatively few stars compared with the disk, it still extends very far into space. Yet even the halo of stars does not represent the full size of the Milky Way. Surrounding the stellar halo is an even larger structure, one that cannot be seen directly with telescopes. This invisible structure contains most of the galaxy's mass and stretches far beyond the visible stars. Astronomers refer to it as the dark matter halo. As astronomers studied the motions of stars within the Milky Way, they discovered something puzzling. The visible stars, gas, and dust in the galaxy did not seem to account for all of the galaxy's gravity. When scientists measured how far stars were orbiting the center of the Milky Way, They expected those stars to move more slowly the farther they were from the center. This expectation comes from the same principle that governs our solar system. In our solar system, the planets closest to the Sun move the fastest, while planets farther away move more slowly. If the Milky Way behaved the same way, stars at the outer edges of the galaxy should orbit much more slowly than those near the center. But observations showed something different. Stars far from the galactic center were moving much faster than expected. Instead of slowing down with distance, many stars in the outer regions of the galaxy were orbiting at nearly the same speed as stars much closer to the center. This pattern appeared not only in the Milky Way, but in many other galaxies as well. Astronomers plotted these measurements on graphs called galactic rotation curves, which show how orbital speed changes with distance from the center of a galaxy. Instead of dropping off at large distances, these curves remained relatively flat. This meant that something unseen was adding extra gravitational pull across the galaxy. If the visible matter were the only source of gravity, stars in the outer galaxy would not be able to maintain their observed speeds. They would drift outward and eventually escape the galaxy's gravitational grip. Yet they remain bound to the Milky Way. The most widely accepted explanation for this mystery is the presence of a large amount of invisible matter. Astronomers call this mysterious substance dark matter. Dark matter does not emit light, reflect light, or absorb light in ways that we can detect with telescopes. It cannot be seen directly, which is why it remained undiscovered for so long. However, its gravitational influence can be measured through the motion of stars and galaxies. Evidence suggests that dark matter forms an enormous halo surrounding the Milky Way. This dark matter halo extends far beyond the visible disk and the stellar halo of the galaxy. While the disk of stars stretches about 100,000 light-years across, the dark matter halo may extend several 100,000 light-years into space. In fact, the dark matter halo is likely the largest component of the galaxy. Most estimates suggest that dark matter makes up the majority of the Milky Way's total mass. The stars, gas, and dust that we can see may represent only a small fraction of the galaxy's true mass. Although scientists still do not know exactly what dark matter is made of, its effects are observed throughout the universe. Galaxies appear to form within large dark matter halos. These halos act like gravitational frameworks that help gather gas and dust, allowing stars and galaxies to form over billions of years. Without dark matter, galaxies like the Milky Way might not exist in their current form. Computer simulations of galaxy formation support this idea. When researchers simulate the growth of galaxies in a universe without dark matter, the structures that form look very different from what we observe. But when dark matter is included, the simulations produce galaxies that resemble those seen through telescopes. In this way, dark matter acts as a kind of invisible scaffolding that shapes the large-scale structure of the cosmos. Despite its importance, dark matter remains one of the greatest mysteries in modern science. Scientists have proposed many possible particles that could make up dark matter, but none have yet been directly confirmed. Experiments around the world are currently searching for these particles using highly sensitive detectors buried deep underground or located in space. Even though we cannot see dark matter directly, its presence helps explain the structure and stability of the Milky Way. It surrounds our galaxy like a vast invisible cloud, extending far beyond the stars we can observe. Understanding this hidden component of the galaxy helps astronomers place the Milky Way in a broader cosmic context. When we compare our galaxy with others throughout the universe, we begin to see that it is part of a much larger family of galaxies. And studying those neighboring galaxies gives us new insight into how galaxies form and evolve over cosmic time. Once astronomers understood that the Milky Way is a galaxy filled with hundreds of billions of stars, another question naturally followed. How does our galaxy compare to the others in the universe? For a long time, scientists did not even know that other galaxies existed. Before the early 20th century, astronomers could see faint cloudy objects scattered across the sky through their telescopes. These objects were called nebulae, which simply means clouds. Some astronomers believed these nebulae were small clouds of gas within the Milky Way. Others suspected they might be something much larger. The question remained unresolved until the 1920s. During that time, astronomer Edwin Hubble studied one of these objects known as the Andromeda Nebula. Using powerful telescopes, he identified Cepheid variable stars within it and measured their distances. The results were astonishing. The stars were far too distant to belong to the Milky Way. Instead, the Andromeda Nebula was an entirely separate galaxy containing billions of its own stars. This discovery dramatically expanded humanity's view of the universe. The Milky Way was no longer the entire cosmos. It was just one galaxy among countless others scattered throughout space. Among those neighboring galaxies, the closest large one to us is the Andromeda Galaxy. Andromeda lies about 2.5 million light-years away and is similar in shape to the Milky Way. Like our galaxy, it is a large spiral galaxy with curved arms filled with stars, gas, and dust. However, Andromeda is slightly larger. Astronomers estimate that Andromeda may contain around 1 trillion stars, possibly more than twice the number found in the Milky Way. Despite this difference in size, the two galaxies are remarkably similar in many ways. Both contain central bulges of stars, rotating disks with spiral arms, surrounding halos of older stars, and massive dark matter halos extending far into space. Together with dozens of smaller galaxies, the Milky Way and Andromeda belong to a collection of galaxies known as the Local Group. The Local Group contains more than 50 galaxies, although most of them are much smaller dwarf galaxies. Some of these dwarf galaxies orbit the Milky Way, while others orbit Andromeda. Examples include the Large Magellanic Cloud and Small Magellanic Cloud, which are visible from the southern hemisphere as faint cloudy patches in the sky. Beyond the Local Group, the universe contains galaxies of many different sizes and shapes. Some galaxies are enormous elliptical systems containing trillions of stars. Others are small irregular galaxies with only a few million stars. Spiral galaxies like the Milky Way are only one category among many. Studying these different galaxies helps astronomers understand how galaxies form and evolve over billions of years. Some galaxies appear calm and stable, forming stars slowly over long periods of time. Others experience bursts of intense star formation, triggered by collisions or interactions with neighboring galaxies. Observations also show that galaxies can merge together over cosmic time. When two galaxies pass close to one another, their gravity can distort their shapes and gradually pull them together. Over millions or billions of years, they may eventually combine into a single larger galaxy. This process has happened many times throughout the history of the universe. In fact, evidence suggests that the Milky Way itself has absorbed smaller galaxies in the distant past. The stellar streams discovered in the halo of the Milky Way appear to be remnants of dwarf galaxies that were gradually torn apart by our galaxy's gravity. These mergers help shape the structure of galaxies and contribute new stars to their halos and disks. Looking outward at other galaxies therefore helps scientists understand the history of our own galaxy. The Milky Way is not an isolated system. It is part of a dynamic cosmic environment where galaxies interact, grow, and change over time. And among all the galaxies in our local region of space, one in particular stands out as especially important to our future. The Andromeda Galaxy and the Milky Way are not simply neighbors. They are also slowly moving toward one another through space. When we look up at the night sky, the Milky Way can appear as nothing more than a faint glowing band stretching across the darkness. For thousands of years, people saw this soft ribbon of light without knowing what it truly was. It looked like a distant cloud, a river of light drifting through the stars. But over time, careful observation and scientific discovery revealed something far more extraordinary. That glowing band is the disk of an enormous galaxy. The Milky Way stretches roughly 100,000 light-years across and contains hundreds of billions of stars. Those stars are arranged within spiral arms that slowly rotate around the center of the galaxy, forming one of the largest structures humans can observe directly. Our own sun is just one of those stars. It sits quietly within a smaller branch of the galaxy called the Orion Arm, orbiting the galactic center at a speed of about 220 kilometers per second. Yet even moving that fast, it still takes more than 200 million years to complete a single orbit around the galaxy. During that journey, the solar system drifts through different regions of the Milky Way, while the galaxy itself continues to evolve. Beyond the bright disk of stars lies the stellar halo, containing ancient clusters that formed billions of years ago. Surrounding that halo is an even larger region of invisible dark matter that helps hold the galaxy together. Altogether, the Milky Way is far larger and more complex than the glowing band we see from Earth. And our galaxy is not alone. The Milky Way is one member of the local group of galaxies, sharing space with dozens of other systems, including the nearby Andromeda Galaxy. In fact, the Milky Way and Andromeda are slowly drifting toward each other and are expected to merge billions of years in the future, forming a new, larger galaxy. But even on these cosmic scales, the Milky Way remains an immense home for the solar system. Traveling from one side of the galaxy to the other would take 100,000 years at the speed of light, far beyond the capabilities of any spacecraft humans have ever built. Yet despite those distances, we are already part of this enormous structure. Every time we look up at the night sky, we are not looking at something far away from us. We are looking outward from inside the Milky Way itself. The stars above us, the faint glow across the sky, and the enormous structure surrounding our solar system are all part of the same galaxy that we call home. And in a universe filled with billions of galaxies, ours is just one small piece of a much larger cosmic story.